I am Ijaz Ahmed. In today's lecture, we shall discuss the Sachs theorem of spectral graph theory. But before stating the Sachs theorem, we shall consider certain definitions. The first definition is how do we define an elementary subgraph? So let's write this definition. Elementary subgraph. An elementary subgraph subgraph, or this is also known as the basic figures. Elementary subgraphs are also known as basic figures of graph. Elementary subgraph or basic figures of a graph G is a subgraph of G. It's a subgraph of G which consists of K2s, that means complete graph on two vertices, and C and cycles. So any subgraph of a graph G whose components are either K2s or the cycles, such a subgraph is known as an elementary subgraph. For example, if we consider a graph of this form, so suppose this is our graph. Okay, let's construct one more here. Then the elementary subgraphs of order. So obviously, when we define the elementary subgraph, which consists of K2s and cycles, and we know that the cycle consists of at least 3 vertices. So an elementary subgraph, so therefore there is nothing like an elementary subgraph of order 1. So first thing is the elementary subgraph of order 1 is not defined. The elementary subgraph of order 1 is undefined. Now the second is the elementary subgraphs of order 2. The elementary subgraphs of order 2 are simply the edges of G, or simply the edges of G. Because we are defining an elementary subgraph, which is a subgraph which consists of K2. So when we define an elementary subgraph of order 2, it must simply be an edge of a G. And similarly, an elementary subgraph of order 3 is a triangle in G. And similarly, we can define the elementary subgraphs of order 4. So let's write this again. An elementary subgraph of order 4 is either C4, that means a cycle of length 4, or a graph H, where the graph H is defined in this way. It is defined like this. It is graph which consists of two components and both components are edges. So therefore, this is an elementary subgraph of order 4 is either C4 or it is an edge. It is a graph edge which consists of these two edges. So now if we look at this graph, then there is no elementary subgraph of order 1, and an elementary subgraph of order 2 is just the edge of G. So therefore, the set of all elementary subgraphs of order 2, this is the set of all edges of G. Now an elementary subgraph of order 3 is a triangle in G. So therefore, this is an elementary subgraph of order 3. So here in this graph, there is exactly one elementary subgraph of order 3, and it is actually this triangle in G. Now an elementary subgraph of order 4 is either C4. So therefore, we can consider an elementary subgraph of order 4 here. It is the C4. This is an elementary subgraph of order 4, but we can also construct an elementary subgraph of order 4 like this, which consists of these two edges and these two components as the two edges. So therefore, we can construct the other elementary subgraphs. We can consider this is an elementary subgraph here. We can consider this edge as well as this edge. So therefore, this is an elementary subgraph of order 4, but we can also construct an elementary subgraph like this. We can consider this edge, and we can also consider this edge. So this is an elementary subgraph of order 4. And similarly, we can consider the other edges also. So therefore, we can consider this edge and this edge. This is also an elementary subgraph of order 4. So in this way, we can see that this graph has many elementary subgraphs of order 4, but there are the elementary subgraphs of order 2 are the edges of G, which are actually 7 in number here. So therefore, the set of all elementary subgraphs of order 2 in this graph G is 7. There is exactly one elementary subgraph of order 3 because this graph is containing exactly one triangle. And there are many elementary subgraphs of order 4. And elementary subgraphs of order 4 are either C4s, which is here. There is one C4 in this figure, but there are many graphs which look like this H in this graph G. So therefore, this is how we define the elementary subgraphs. Now again, we shall state one theorem that we have done in the previous lecture. In that theorem, we had discussed the determinant of an adjacency matrix of a connected graph G. So let's recall that theorem first. Theorem. That theorem states that let G be a graph with vertex set V is equal to 1, 2, up to n. Suppose this is our finite graph G, and let A be the adjacency matrix of G. Let A be the adjacency matrix of G. Adjacency matrix of G. And then the determinant of A. Then this determinant of A, this is equal to summation -1 power n minus C1 of H minus C of H into 2 power C of H, where the summation, where the sum runs over all spanning elementary subgraphs. Spanning elementary subgraphs of G. Elementary subgraphs of G. This C of H denotes elementary subgraphs. The sum runs over all elementary spanning subgraphs H of G. And C of H denotes the number of cycle components in H, cycle components in H, and C1 of H denotes the number of components in H. Denotes the number of components in H. So therefore, if we have a graph G consisting of these n vertices, which are labeled as 1, 2, 3 up to n, and A is the adjacency matrix of G, then the determinant of A is given by this formula, where the sum runs over all elementary spanning subgraphs H of G. This notation C of H denotes the number of cycle components in H, and the C1 of H denotes the total number of components in H. And this n is the number of vertices in G. And this theorem was done in the previous lecture. And now we are ready to state the Sachs theorem. So theorem. This is the Sachs theorem. Let G be a graph of order n. Let G be a graph of order n with characteristic polynomial of G as this P G lambda. And suppose this is defined as this lambda power n plus A1 lambda power n minus 1 plus A2 lambda power n minus 2 plus so on plus an minus 1 lambda plus an. Suppose this is the characteristic polynomial of the adjacency matrix of the graph G, then the Sachs theorem actually states what are the values of these ai's. Then Sachs theorem tells us that this ith coefficient ai, this is given by the formula summation h belonging to hi minus 1 power p of h into 2 power c of h into 2 power c of h, where hi is the set of all basic figures. Is a set of all basic figures H of G of order I. So therefore here this HI, this is the set of all basic figures H of G that have order I. Now here this notation P of H, this P of H denotes the number of components in H, denotes the number of components in H, and C of H denotes the number of cycle components in H. Denotes the number of cycle components in H. So here actually we have a little refinement. So here we have defined this C of H is the number of cycle components in H, and C1 of H, this does not denote the number of components in H, but this denotes the number of K2s in H. So we will correct it, denotes the number of K2s in H. denotes the number of K2s. K2s in H. So here we have this little correction. We are given this determinant of the adjacency matrix is given in this way, where C of H is the number of cycle components, and the C1 of H. This denotes the number of K2s in this elementary spanning subgraph H. And similarly, we have here this HI is the set of all basic figures of order I. This P of H denotes the total number of components in H, and the C of H denotes the number of cycle components in H, while H is an element of HI, while HI is the set of all basic figures of order I. So now let us do the proof of this theorem. Proof. Now suppose, if lambda power n plus a1 lambda power n minus 1 plus so on plus an is the characteristic polynomial. So if this is the characteristic polynomial of A, characteristic polynomial of A, while A is the adjacency matrix of G, while A is the adjacency matrix of G. Where A is the adjacency matrix of G. Then from matrix theory, this AI, we know that this I component AI, I coefficient, is given by minus 1 power K. It's actually minus 1 power I times. This AI is minus 1 power I times the sum of all principal minors of order I. So this is given from the matrix theory. If we have the characteristic polynomial of a matrix A, then this A1, we know that it is the trace of the matrix, or it is just the sum of all principal minors of order 1. And similarly, when we have A2, then that will be the sum of all 2 cross 2 principal minors. And here, it will be from the matrix theory, this A2 will be the sum of all 2 cross 2 principal minors and minus 1 power 2 and so on. So therefore, this AI in this characteristic polynomial of A, then AI will be given by minus 1 power I times the sum of all principal minors of order I, where I runs from 1 to n, where I is equal to 1, 2, so on up to n. But now if we look at this AI, if we look at this principal minor of order I, now this principal minor of order I from the matrix A, where A is the adjacency matrix of G. By this principal minor of order I, we mean the determinant of a submatrix of A, where A is the adjacency matrix of G. Now here by principal minor of order I, here by principal minor, here by principal minor of order I, we mean the determinant of a square submatrix. We mean a determinant of a submatrix we mean a determinant of a submatrix of A, which is induced by some I vertices of G, which is induced by some I vertices of G. I vertices of G. So actually, if we consider an induced subgraph of G, which is induced by some I vertices of G, and then construct its adjacency matrix, that will be same as the principal submatrix of order I from the matrix A, where A is the adjacency matrix of G. So here, when we consider this AI, so this AI is minus 1 power I times the sum of all principal minors of order I. And this principal minor of order I is just the determinant of a submatrix of A, which is induced by some I vertices of G. So therefore, from the previous theorem, when we had this principal submatrix of order I, it is the determinant of an induced subgraph of G, which is induced by some I vertices. So therefore, here we can invoke the previous theorem that we had stated earlier, and that using this theorem, now we can evaluate the determinant of that principal submatrix of order I. So therefore, the previous theorem, so thus by previous theorem, the determinant of such a principal submatrix is given by as minus 1, this is actually minus 1 power I, minus 1 power I minus C1 of H minus C of H into 2 power C of H. Here we are writing this I because we are considering a principal submatrix of order I. So therefore, it is induced by a subgraph of G, which consists of some I vertices. So therefore, now using this statement that AI, it is minus 1 power I times the sum of all principal minors of order I. So therefore, this AI, this will be equal to minus 1 power I, then the sum of all principal minors of order I. So therefore, this is summation H belonging to HI, because we know that this HI is the set of all induced elementary subgraphs of order I, and this is minus 1 power I minus C1 of H minus C of H into 2 power C of H. Now here we need some calculations. We can take this minus 1 power I outside of this, or we can multiply inside this minus 1 power I, then we will get minus 1 power 2I. So therefore, this is just equal to minus 1 power 2I, then summation H belonging to HI minus 1 power minus C1 of H minus C of H into 2 power C of H. Now, this minus 1 power 2I is equal to plus 1. And here we can write this is equal to summation H belonging to HI. Now this can be written as minus 1 C1 of H minus 1 C of H. We can take this minus 1 common. So we can write it like this. This minus 1, then here we can write plus in this way. So therefore, this is minus 1 power minus P of H. Or this is not actually minus P of H. So if we raise the negative quantity to minus 1, or we raise the positive quantity to minus 1, it remains invariant. So therefore, we can just write minus 1 power P of H. So this C1 of H plus C of H, while we know that the C1 of H is the number of K2s in H, and C of H is the number of cycles in H. So therefore, the C1 of H plus C of H, is the total number of components in it. So therefore, this first term is minus 1 power negative times the number of components in it. But we will here just write this minus 1 power p of h, where p of h denotes the number of components in h, because we know that this minus 1 power k will be same as minus 1 power minus k. So then we have this 2 power c of h. And so therefore we have completed the proof where the summation, where the sum is over all the elementary subgraphs over all elementary subgraphs H of G with I vertices. So this completes the proof of the theorem.